Welcome to the Health AI Brief, breaking down the AI shaping our world one concept at a time. When we train a junior colleague, we give them textbooks and guidelines, but most importantly they see patients. They see hundreds of chest x-rays, listen to countless chests, and over time, from all that data, they build an internal framework for recognizing things like consolidation or a pleural effusion. That internal learned framework is what they use when they next see patients. In the world of AI, we hear about training an AI, but what is the thing that's actually being created? When an AI is trained on 1 million retinal scans, what's the specific output of that process? This is where the term model comes in. The model is essentially the end product of the training process. It's the piece of software that's learned to perform a specific task. It isn't the raw data and it isn't the training algorithm, it's the result of those processes. It's the distilled knowledge captured in a digital form. I think a good analogy is the training of a sniffer dog. The dog is given hundreds of samples to smell. The training process uses rewards to help the dog's brain create and strengthen the neural connections needed to recognize a specific sense. The model here is that final trained network in the dog's brain. It's the thing that can be deployed in an airport to check new bags. It takes a new input, the air from a suitcase, and produces an output, sitting down or walking on. An AI model is the same. Let's say we're building a model to detect fractures on wrist x-rays. We feed a learning algorithm thousands of images, each one labeled fracture or no fracture. The algorithm then adjusts millions of internal parameters, gradually learning the specific patterns of pixels, lines, and shadows that signify a break. The final saved set of those optimized parameters is the model. It's a self-contained mathematical black box that can now be given a brand new unseen wrist x-ray and in seconds produce a prediction, fracture or no fracture. It's the engine created through training that does the actual work. So why does distinguishing the model matter in our day-to-day work? Firstly, it highlights that a model is just a static snapshot. The model you use in any product in clinic today was trained on data at a certain point in time and is then frozen. It doesn't typically learn on the job. This is a safety feature, but it can also be a problem. If imaging technology changes or a new disease variant emerges, the model's performance can degrade because its knowledge is out of date. This is called model drift, and we need to ask if there's a plan to monitor and retrain the model over time. Secondly, it reminds us that the model isn't the whole product. An incredibly accurate model for detecting a pulmonary embolism is useless if the software's clunky, doesn't integrate into our imaging workflow, and produces alerts 3 hours late. The model's the engine, but we have to evaluate the whole car, the user interface, the speed, the safety features, and how it fits into our very human way of working. And third, similar to the previous episode, it forces us to scrutinize the training data. Our model's a direct reflection of what it was trained upon. If a skin lesion recognition model was only trained on images of fair skin, it will almost certainly perform poorly and dangerously on darker skin. The model itself isn't biased, the data used to create it was. So when you're appraising a new tool, the first question must be, what specific data was used to train and validate this model? And does it reflect my patient population? So that's models in a nutshell, the finished product of training, the engine that makes the predictions. If you found this useful, please hit subscribe or follow in your podcast app so you don't miss future episodes.